Today we're going to cover a new chapter. An interesting topic is a transmission line. So chapter 13. We have 4 topics. The first topic is the basic characteristics of a transmission line. The second topic is something unique happening inside transmission line. And the third will be the transmission line. Also something very unique can be used as a inductor or capacitor. So that's the third topic. The fourth topic will be the little calculator called Smith chart, which can calculate the combined impedance of a transmission line plus the load, usually the antenna. So fourth topic, let's get started for the first one. 463. So first topic is what exactly is a transmission line? A transmission line generally refers to a conductor will conduct a signal of a very high frequency. So, for example, frequency of gigahertz. So in that high frequency, gigahertz, the wavelength for 1 gigahertz is 3 meter. So the wavelength of 1 gigahertz is actually 0.3 meter. 0.3 meter. So the wavelength is really short, 0.3 meter. That's about 1 feet. So if you think about it, that means for a wire of 1 feet long, that's about from here to here, the voltage on this transmission line will be different. Think about it, because we are sending out, for example, sine. So if you can visualize, the voltage is like a sine. So if you measure the voltages at different locations, the voltages are actually different. So that's what's unique about transmission line. That's what's unique about the signal at higher frequencies, because the lambda, the wavelength, is very short, and you get something unique happening. Conventionally, when we talk about signals of several thousand hertz or even megahertz, the wavelengths are miles or thousands, hundreds of miles long. So you do not usually care about this voltage distribution over several hundred miles. But with transmission line, with signal frequency in gigahertz, you have to, because a lot of the conductors are longer than 1 feet long, 0.3 meter long. So the voltage and current can be different at different locations on the conductor. So that is why we have to study transmission line, because something strange will happen, something unique will happen. So once we figure out why we want to study the transmission line, the first topic is the different types of transmission line. That's the 4 different types. The one on the lower right corner is a twisted loop, twisted pair. This is a very common coaxial. This is a parallel. There's another parallel, but has different impedances. We'll talk about impedance. So for transmission line, it turned out the resistance became not important. Yeah, a conductor 1 feet long, we really don't worry about the resistance, because resistance is extremely low. We're not talking about conductor 100 miles long or 100 feet. Then you started to care about resistance. Now, with a short distance, so the resistance is not what we care about. What we care about instead is the inductance and the capacitance. The inductance and the capacitance make this transmission line and reactive wire. So you have capacitance between the two wires. You have a magnetic field. That means the inductance of this conductor. So the inductance capacitor used to be neglectable. Now it became significant. So that's the first topic. The second topic we also talk about is the different type of connectors for transmission line. They have all kinds of connectors. This will be the type F. So there's a BNC connector. This is another connector. This is a type N. This is type F. Okay. So there's all kinds of connectors for different applications. That's RCA. That's another transmission line connector. So they got different connectors. And that is a model of transmission line. So this transmission line has resistance, has capacitance, has inductance. In the low frequency range, the inductance and capacitance are insignificant. So, and so does resistance even. So we just think about those as conductors. At higher frequencies, those inductance and capacitance became more and more significant. Not the resistance, because the distance is generally not very long. We don't use transmission line generally transfer long distance energy. So resistance is insignificant. The conductance and the capacitance became more significant. When we have alternating signals, it will energize and de-energize those inductors and capacitors. And it became an oscillating effect. So you will energize it, energize the other, energize. So while you have power connected on one side, the inductors will keep energized, take turns to energize. So it needs some energy to energize those capacitors and the inductors. And those energy needed to energize those inductors and capacitors, we use a characteristic impedance characteristic. So the next topic will be characteristic impedance. Characteristic impedance is calculated based on the inductance and capacitance. So this is the equation to calculate the characteristic impedance. In this cable, a very common cable, the characteristic impedance based on the design, the kind of insulating material, and the dimension of the cable is 50 ohm. So that's a very common one, characteristic impedance. So basically, characteristic impedance represents how much energy we need to basically charge this transmission line, energize this transmission line, energize all the way to inductors and capacitors. So that's a characteristic impedance. So when the power is connected from the one side, the other side will not receive the signal unless all those inductors and capacitors are energized. So the signals will travel slower. That's the next topic called the velocity factor. Because of those inductors and capacitors, it will really slow down the signal speed. So instead of traveling at the speed of light, which is 300 millimeter per second, it's travel a little bit slower. how slow it is, it will be called velocity factor. So if a velocity factor is 0.5, it will be half the speed of light in vacuum. So that will be half of this. If the velocity factor is half, generally the velocity factor is between half and 0.9 for a typical transmission line. So it will be up to half the speed of, so it will be slow. To extreme, it's only half the speed of the speed of light. Right, that's another topic, velocity factor. The last topic will be the energy loss. So the transmission line does have losses based on the distance. So this is the attenuation for 100 feet of transmission line. So that's a different type of transmission lines. Looks like the last one has the best performance because the loss is only 1.3 dB. If the loss is 1 dB, that means zero loss. If loss is 2 dB, it means half the energy wasted. Not 2 dB, 3 dB. If loss is 3 dB, it means half the energy is wasted. So for 100 feet of cable. So that gives you an idea. For example, the worst one will be this cable. It's called the RG58A/U. So that will be the worst performance transmission line as far as energy loss. So after 100 feet, you get some energy loss. So those are the 1, 2, 3, 4, 5 topics for the first section of transmission line. The second topic of transmission line will be the standing waves. Well, if you look at the water, the waves will travel forward. And if you watch the wave, if the wave will hit an obstacle, the wave will bounce back. Same thing happens inside transmission line. A AC signal, so we will study this using 4 different scenarios. First scenario is matched. Second scenario is shorted. Third will be open. Last will be the mismatched, which is the most common case actually. The other two are very common also. Okay, so let's first look at the matched. Matched transmission line means the transmission line is terminated with a load with identical resistance as the characteristic impedance of transmission line. So if the characteristic impedance of transmission line is in this case 50 ohms, we will have a 50 ohm resistor. So this is called a dummy load. A 50 ohm dummy load will be connected to the other end of transmission line. So what happens is you have a power supply, and the power supply will have a 50 ohm impedance also. So everything is matched. Power supply has 50 ohm resistance, and transmission line has 50 ohm characteristic impedance, and the load is 50 ohm. So what happens in this scenario is once you turn the power on, half the voltage is on internal, the half is used to energize this coaxial cable. So as the energize goes on at the speed of light, multiply the velocity factor. So this travels slower than the speed of light, but it still travels very fast. For example, 80% of speed of light. So as it travels, the voltage half here, half is used on the cable, energize the cable. So when it reaches the load, it is as if you have an infinite cable. This 50 ohm will completely absorb those energy. So you have half the energy on the generator, half the energy moving forward, and completely go to ground. So that is in a lot of cases, best scenario. That means we have a matched transmission line to the source and to the load. And we also know in this scenario, we have maximum power transfer from source to load. So maximum power will be delivered from here to here through this transmission line. So a lot of time, this will be the ideal scenario. There is no reflection because the 50 ohm just burns out all the energy as a heat. The 50 ohm can be an antenna. If it's an antenna, it will radiate those energy out to the space. So those 50 ohm will never, those energy will one direction. There's never energy bouncing backwards. So that's a scenario number one. So there's a zero standing wave. So that's the best scenario. The second scenario will be the shorted line. So on the other side end of the transmission line, we actually create a short. We connect them. In majority of our circuits, low frequency, you never want this to happen. But in higher frequency signals, because the inductive components on the transmission line, you can actually do it. You can short the other end of transmission line. And let's look at what happens. When you short here, what happens is the voltage, the red one, voltage will be zero because you shorted. But the current will be maximum. Why? Because you shorted, you had maximum current. But usually if you shorted, the current will be infinite. In this case, the current is determined by the characteristic impedance because there's no ability to transfer infinite power because of the limitations of those inductors. Those inductors are also called chokes. So those chokes will choke out the current. So there's no infinite current here. Instead, there's a current which is voltage divided by the 50 ohm. That's with current maximum. So you have voltage, zero current, certain amp, for example, 2 amp or 3 amp. And then what happens, the voltage is just like a wave. You have waves, so that's the wave. That's assuming the signal is at very high frequency. So that's the signal frequency. That's signal frequency. You have the half wave. This is called standing wave. Why it's called standing wave? Because the voltage is always zero. The voltage here is always maximum. This is the amplitude of sine. So here you have zero sine. Here you have a little sine, and here you have the maximum sine. And so does the current. Here is the maximum sine current, and then suppose this is sine source. So you have a zero current here, and zero current here, maximum. So it ended out, if you have maximum voltage, you have zero current. So that's what happened. So you go backwards, and then on this side, you will have a voltage and a current, and that is the combined impedance of a transmission line and a short. So from the source perspective, this is the combined impedance of short and transmission line. So we can also leave the other side open. So this case, you have the maximum standing wave. That's called the standing wave. And so does the open. We can also leave the other side open. When the other side open, we will have peak voltage and zero current because it's open. So there's no current at this location from here to here. There's no current. But it doesn't mean there's no current at the other part of the transmission line. Because the wavelength is so short, so the current literally just going on inside those wires. The electrons are compressed and expanded. The density of electron, if you think about it, on both wires, the density of electron will be compressed and relaxed, compressed and relaxed. That's what's going on here. When we have the peak current right here, we have the maximum swing of the compression of the electrons and the release of the electrons. And then we have the minimum swing of current right here. Current will be 0. Of course, when the current is 0, we actually have the maximum potential swing. So that means at this location, the electrons not moving because current is 0, electrons are moving. But the potentials of those electrons are having a big swing. So it's kind of strange. You have maximum potential, but the electrons are not moving. The potential has a up and down. That means AC. You have a maximum potential right here. So you have a maximum current here, and you have maximum voltage here. So the current is alternating, so does the voltage. So it's a standing wave. So that's the current. So maximum current right here and the maximum voltage when they have 0 current. So that is another topic. So you have the peak voltage and minimum current. So that's it for the open. So as far as the source is concerned, the source is seeing this. So that's the voltage the source sees. That's the current the source sees on the transmission line, on the load. So that's the load characteristic of the transmission line with an open on the other side. The last topic, so they have a maximum standing wave in this scenario also. The last scenario will be somewhere in between. So what happens is you have a power, you have a transmission line, source transmission line, and then you have a mismatched load. It's either open, nor short, nor identical matched. It's mismatched. In this scenario, mismatched, we will have a certain degree of standing waves, somewhere between 0 and maximum. That will be. So we have a standing wave ratio. If Z1 and 0 equal, standing wave ratio equal to 1. That's the ideal situation. Standing wave ratio equal to 1. If it's different, then the standing wave ratio will be higher than 1. That will be non-ideal. Obviously, the higher the standing wave ratio, the worse the worse it will be, because you have this is a standing wave ratio as infinite. So that means you have maximum standing waves. This is a general. That means this will represent what the load is, the voltage and current right here represent the load characteristic. Then if you go backwards, and that will be the characteristic of the transmission line combined with load as far as to the source is concerned. So now we think about this circuit is, instead of thinking this circuit has 2 components, the load and source, now we have many components in between. These components are inductors and capacitors, inductors and capacitors. So think about, we have all those inductors and capacitors. So if you have AC power energized on one side, and you have oscillations all the way to the load. So as far as the source is concerned, sources the impedance sources C is different from here. It's something else because all the inductors and capacitors we are dealing with when the signal travel from here to here, from left to right. So that is why we actually the last topic. Let's move to last topic. The last topic is the Smith chart. Smith chart is a chart invented in the 30s by an engineer called Smith. So this is the Smith chart. The purpose of Smith chart is just that. Figure out the combined impedance of load plus the transmission line to the power supply. Because in the old days, we have just two components when we analyze circuits, source and device, source and the load. Now we have to take care of the transmission line. Also, there is a third component. So the Smith chart is basically how we can quickly estimate the combined impedance of the load plus the transmission line to the source. And that can be very handy using Smith chart to quickly estimate the combined impedance of, let's do an example of transmission Smith chart. So if they say we have a 20 feet transmission line, 24 feet transmission line, the signal is 140 megahertz, very high frequency compared with the length of this cable. And the resistance of the load is 93 ohms. So it's a 93 ohm resistance. So find the combined impedance of the transmission line plus the impedance here. I will skip the details of how to use the Smith chart. Basically, you start with this 93 ohm. Where is 93 ohm? Right here. You start in 93 ohm and you draw a circle, and then you will travel the circle based on the 20 feet distance. So you travel here, here. I think this direction, travel backward. From if you go from source to the load, you travel one direction. Go from load to source, you travel the opposite direction. So you started here, you travel 24 feet, and ended here. That will be the combined impedance. So you started with your load. That's your load, 93 ohm load. 93 ohm, then you travel on this red circle 24 feet. 24 feet. That's the length of the cable. After you travel 24 feet, you arrive here, and that's your combined impedance. Let's do another example. Another example is again 24 feet cable. The load is this. Load is this. So now we will have the load which start from here. So that's where the load is. Instead of 90 ohm previously, a pure resistor right here, now we have a load which is 40 ohm plus J30. So that's the load location. So now, again, same direction. You will travel 24 feet and ended up here. So if you started here, you probably ended up here. But you started here now. Now we started here. So again, travel 24 feet in the direction to the source. That will be the direction to the source. If you travel from source to load, you will travel that direction. So now we travel 24 feet. Okay, we stop here. That will be the combined impedance, which will be combined impedance will be right here. Combined impedance will be 93.6 minus 28 J. So Smith chart is an excellent way to quickly estimate the combined impedance of the transmission line, because now we have two components besides the power supply. So you have to combine the two as one single impedance. How do you combine them? You can either do it manually, mathematically, which takes a long time and prone to errors, or you can use Smith chart. The reason I did not go to the detail of Smith chart is, well, you will forget when you, the detail is easy to learn when you're really working in this field. Otherwise, it's very easy to forget about that detail. Anyway, all you need to know is you start with your load impedance, whatever your load impedance is located on this chart. It can be here, 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 wherever. And then you draw a red circle. That is the SWR equal to 2 circle. And then you just travel whatever. So if the cable became 48 feet long, so if the cable is 48 feet long, you need to travel twice the distance. So you started from here. Instead of 24 feet, you travel 48 feet. That's double the amount of traveling. So you probably will end up here, yeah, somewhere here, because you are running in circles. So for 48, you just ended up somewhere here, 48, 50, whatever distance. So you can get the combined impedance of a transmission line, whatever the length of that transmission line is. You can combine the impedance together as a one single impedance to the source. Then you can analyze what the power distribution, whatever. So that's the Smith chart. So we take care of 3 topics. First is the basics. Second is the standing wave. That's something unique happens inside transmission line. Being the voltage and the current will be different. When you travel along the transmission line, you measure the voltage and measure the current. It turned out the voltage and current will be different on transmission line. Ideally, it will be the same, half the voltage. That's ideal. The voltage everywhere here is flat. There's no standing wave. That's ideal scenario. But in most cases, non-ideal scenario, when you measure the voltage across the transmission line, you get the up and downs. And those up and downs are called the standing wave. So that's one case, another case, and another case, the standing wave. And the standing wave, the relative size of the standing wave can be calculated based on this standing wave ratio. So you can find the standing wave ratio based on the load impedance and the characteristic impedance of your transmission line. You can find the standing wave ratio. And also you can find the reflection coefficient. The reflection coefficient can be calculated as a reflection coefficient. Yeah, this is how you calculate the reflection coefficient. It's also based on the 2 impedance of characteristic impedance and the impedance of the load. So you can calculate how much energy is reflected. They call the reflection ratio. Reflection coefficient, whatever name, reflection coefficient. So once you get a reflection coefficient, you get an idea of how much energy is bouncing backwards. And also you can calculate, of course, the standing wave ratio. It gives you an idea how much standing wave is on the transmission line, standing wave. Generally, this is a general case where you have a certain standing wave of voltage and current. So it's always the case, not always the case where the actually peak and the minimum overlay, not always the case because you not always have the pure resistors here. You may have inductive component here or capacitive component here, so it will have a phase angle difference of the standing wave. Anyway, you have maximum and minimum current, you have maximum minimum voltage. They don't always match perfectly here because the load can be different, causing a phase shift of the standing wave of current and voltages. In this case, they perfectly match. In this case, they perfectly match. In the ideal case, there's 0. So that brings us to the last topic of this transmission line, which actually we did the Smith chart. Smith chart is very good, quick and easy to find. Once with a little practice, quick and easy. That's true. But today we got computers. Computers even quicker and even easier. So with computers, we can do this Smith chart calculation even faster, even quicker. But before the computer were invented, more common, this was invented in the 30s, 1930s. Almost 100 years old. The last topic of transmission line will be the transmission line can be used as inductors or capacitors, or both inductors and capacitors. So, so it turned out transmission line, when it is short or open, this is short, this is open, this is short, this is open. This is the length of your transmission line. This is the combined impedance of your transmission line. So at quarter wavelength, if it's short, if the transmission line is shorted, it will have maximum impedance, unlimited and maximum. If it's open, it has zero impedance. How about half wavelength? If the transmission line length is half the wavelength, open has infinite. You will think open always has infinite highest impedance, but turned out in the quarter wavelength, open has minimum. But at half wavelength, the short has zero impedance, and open has maximum. So that's kind of strange scenario for transmission line. And this can be used as inductive component. So you can have quarter wavelength or half wavelength of transmission line, or somewhere in between. You can create a XL, whatever XL you needed. So if you need an infinite XL or zero XL or somewhere in between, you can just use a transmission line like this. And the length is determined by whatever impedance you wanted. This is unbalanced, this is balanced. So for unbalanced, you have ground, and that's the transmission line. So for balanced, you have ground and two transmission line. So when you energize this balanced transmission line, the length will determine the combined impedance of the equivalent impedance. So instead of build an inductor, build a capacitor, in this transmission line can be used as inductor and capacitors. And another example is here. This is buried, sandwiched in between the two ground plane. You have two ground plane, and this is an advantage over the previous case because the transmission line is insulated within, sandwiched inside, so there's no radiation. Compared with this case, the transmission line potentially can be antenna. Radiation happens, you can have energy loss, and you create noise to other components close by. So this is alternatively, this is obviously better. So just by controlling how long, this is a cross-sectional view. So this is like looking at the transmission line vertically. Transmission line go into the paper. So if we turn it sideways, that's what it looks like. And so that's how we energize the transmission lines, one single wire. And by controlling the length of the transmission line, we can make that transmission line as an inductor, as a capacitor. This is an inductor, as a capacitor, inductor, capacitor, or as at resonance, at 0 ohm, or serial. This is called a parallel resonance. This is called a serial resonance. So as a inductor and capacitor in parallel, or inductor capacitor in serial in resonance. So you can use that transmission line as reactive components. Instead of building inductors and capacitors, all you need is have a little strip of wires printed on the circuits, and use that little strip of wires as the tuner or as the filter, as a reactive component. So that's our last topic. So as inductor and capacitor. So obviously all those happens at high frequency. that means we are talking about hundreds or thousands or tens of thousands of megahertz. So in that frequency range, we have a characteristic impedance, we have a velocity factor, we have standing waves if it's not mismatched, or short and open. We have short and open. In this case, a special case of short and open. This is actually a special case of short and open. We can use this short and open transmission line as a reactive component. That means the inductors and capacitors, we don't have to build inductors and capacitors. We just use transmission line. It performs as an inductor or capacitor because it is inductor and capacitor. Inductor is something convert electrical energy to magnetic energy. A transmission line does exactly that at high frequencies. So that's a third topic. The fourth topic will be a little graphic calculator help us to estimate the combined impedance of load and transmission line. So transmission line plus load, we can estimate the combined impedance. For example, give the author's example, you have 90 ohm here, you have 58 ohm here, transmission line is 50 ohm, load is 90 ohm, what is the combined impedance? That's the example for 24 feet. Let's find the result. 24 feet of that cable of transmission line. The combined impedance, 24 feet of 58 ohm, 50 ohm transmission line, with a 90 ohm resistor, and 93 ohm. The combined impedance will be this 93.3 minus J 30 ohm. So that's the combined impedance. It's not a pure resistor. It's actually a capacitive. Why capacitive? Because it has a negative imaginary part. So it's a capacitor, a capacitive. So this whole thing looks capacitive to the load. And obviously, the load impedance depends on what load impedance is. Load impedance, output impedance is. You can find the current and the voltage and the power and all those things. So that's all the subject. The subject is pretty complicated because it's unconventional. It's something we don't familiar with. We as electrical engineers, we use to analyze DC power. We use to analyze AC power at 60 hertz. That is for 60 hertz, the lambda is hundreds of miles. If you do the math, 3 point divided by 60. So that is how many miles, I would say thousands of miles, if not hundreds of thousands of miles long. So the lambda wavelength is really long. So you have to able to travel that distance to find the standing waves, to use it as reactive component, or to use Smith chart to evaluate the combined impedance. So that kind of long wire is not very common. We don't use that. We have wire maybe 10 miles long. So we just skip that because it's in at least hertz, 60 hertz, there's zero differences. There are differences, maybe 1 out of a million percent differences. So we don't care. But as frequency goes higher and higher to gigahertz, now it became so significant, and that is the subject we analyze. And it's important because this kind of signal, 1 gigahertz, 3 gigahertz, is exactly the most commonly used signals for today's information age. The cell phones, the Wi-Fi's, the cable modems, the DSL modems, they all use this frequency. So that's why this subject, although it's unconventional, but it's it's some knowledge we should have. So hopefully those 4 basic subjects will get you started on this subject. So that's all I have for today, and I will see you guys next week.